So, topic 10.1, the basics of organic chemistry. And you can see there just about what we need to cover in this section. And we start by looking at what a homologous series is. So, a homologous series is a kind of family of organic compounds, and they have the same general chemical formula, but they show a gradation in their physical properties. So if we take one example here of the alkanes, you can see as I move down the homologous series, I'm essentially adding in a CH2, because what I'm doing is I'm getting the chain longer. So that's methane, and I'm lengthening the chain each time by a CH2 unit. There's ethane, and then, oops, those are all H's. There's propane, like that. And as I go down that series, the gradation of physical properties, something like their boiling point, because we're getting longer chains, we're getting better London forces, so we see an increase in their boiling points. Structural isomers, they have the same molecular formula, but when we draw them out, they look different. And you can see an example here. This is butane, C4H10. This is also C4H10, but we would call this 2-methylpropane. And you can see if you imagine those modeling kits disconnecting things and putting them back together, that's us getting structural isomers. We can do similar stuff where we've got double bonds. If we move the position of the double bond, we end up with another isomer. Interestingly, using that C4H8, another isomer would be a cycloalkane. There's a ring structure there. These are the functional groups that we need to be familiar with, and you can see that some of them have been assigned general formula. So if we know here we've got 5 carbons and it's an alkene, we'd expect to see 10 hydrogens. So you can look through those. These functional groups are characteristic of their homologous series, and these functional groups are kind of the bit that does the interesting chemistry in the molecule. So alkanes, really, you'll see in the next topic that they do free radical substitution and we can burn them, but there's not much going on. Whereas in an alkene, we've got that double bond, and that's going to be quite reactive for us. So there's the functional groups, and there are some suffixes that will help with the naming of compounds that include them. Here's some rules on how to name. Really, the best thing is to practice and look at some examples. So we can count up longest carbon chain that includes the functional group. So if we find that our functional group is at the end of 3 carbons, then it's going to be prop something. We then need to look at what the functional group is and think of that last slide. Well, what's it going to be ending up with at the end of the name? And then we have to show what else is on the molecule and where the functional group is. That's what this piece here is about. So overall, when you tag all those bits together, that's how you'll build up a name. There's some examples that you can work through and have a look at. Some quite complicated, but you can see how we've been looking at longest functional groups that include our longest carbon chains that include our functional groups, and then we're looking at naming the pieces that go with it. Okay, where do we get to? Here we go. Right, so as well as naming these organic compounds, we can identify substances as being primary, secondary, or tertiary in the case of halogenoalkanes and alcohols and amines. So we need to look at where that functional group is and the carbon that it's attached to. And if that carbon has 2 or more hydrogens on it, as we see here, then we describe that molecule as primary. If it's only got 1, it's secondary. If it's got 3, then we describe it as tertiary. Now, the reason we count, well, the description here is in terms of the hydrogen atoms, is because there is one example of a primary halogenoalkane that's got 3 H's on. That would be the methyl version. So a shorter way that some people like to do it is they look at the number of carbons attached. So if we ignore this example, then a primary has 1 carbon attached to the carbon, attached to the Cl there. A secondary has 2 carbons attached to the carbon with the Br, and a tertiary has 3 carbons attached to that with that. So if you were to ignore this one case, you could use that as maybe an easier way of remembering what's going on, because primary would suggest 1, secondary suggests 2, and tertiary suggests 3. And we can do something similar if we're dealing with alcohol, so there'd be an OH there, or if we're looking at having the amine group, which is NH2, and we start switching out some of those H's for additional C's as well. So it's a little bit different. So for example, a secondary amine would be where we've got our N and maybe some methyl groups like that. That would be a secondary amine. You can see that it's still fitting our idea of 1H being attached, but this time we're looking around the N rather than the C that's attached to the functional group. Last piece, benzene. So benzene has this delocalized system of electrons, which gives it quite unusual properties. And so we've got an alternating system of single and double bonds, and if we were to draw that flat, the reason being we have overlapping p orbitals, so my pi bond can delocalize around there like that, and it gives it a lot of additional stability. So if we were to look at enthalpies of hydrogenation, which is where we add hydrogen to a substance, we can get data for adding H2 across 1 carbon-carbon double bond, and let's say that gives us X kilojoules of energy coming out of that. Now, if we've got 3 double bonds, we would maybe expect the enthalpy of hydrogenation here to be 3x, but it turns out it's less than that, and it's less than that because it's already stabilized by this delocalized system. We can also see that bond lengths are all identical. We've not got longer bond, shorter bond, longer bond, shorter bond, longer bond, shorter bond. They're all the same, and it also prefers to undergo substitution over addition. So something like, again, ethene would very happily decolorize bromine water to form that dibromo compound. The benzene rings tend to undergo substitution reactions to avoid losing their delocalized system of electrons. Right, that's what we've covered. Thank you.